Minimum phase system. All the poles of a causal stable system are inside the unit circle. However, the zeros could be everywhere. If all zeros of the system reside inside the unit circle, it will also be called minimum phase system. It is very useful when finding the inverse system, causally and stably. See figure 5.23. Okay? Here you see the original signal and the main signal, h of n. We would like to introduce inverse system. Okay? So two systems, the first one h of n and its inverse, the second one. Okay. To have an objective system, it's necessary that the final output be equal to the initial input after passing through two systems. That is, y of n is equal to x of n. Y of n is the output and x of n is the input. Okay? H of z is usually mandatory in the path of the input signal, but the reverse system is designed to neutralize the effect of the original system. To satisfy it, h whole of n is equal to delta of n, an impulse response, a Dirac. So impulse response, the main impulse response needs to be convolved with h inverse of n. The result should be delta of n. It means that we should have h whole of z be equal to 1, which is equivalent to h of z times h inverse of z. That is, the poles and zeros of the reverse system must be equal to the zeros and poles of the original system respectively, but in the inverse manner. Okay? Here you see the idea. There is a zero at location 0.5. So, for inverse system, it should be whole. And another zero at location 1.5, it has been converted to pole. Okay? And moreover, a pole, a complex conjugate, has been converted to zeros, the same location. So, you are going to be familiar with the idea of inverse system or inverse filter. The above figure shows a system with zero outside the unit circle where h of z is equal to 1 minus 0.5 times z minus 1 multiplied by 1 minus 1.5 z minus 1 over 1 minus z minus 1 plus 0.5 z minus 2. Okay? And we have h inverse of z is being equal to 1 over h of z. It is understood that in no case h inverse of z can be both stable and causal because one of its poles is outside the unit circle. Okay? Now, for the inverse of a system to be both stable and causal, not only its poles but also its zeros must be inside the unit circle. Such a system is called a minimum phase system. That's the idea. If it's not a system with minimum phase, it can be considered as a sequence of two systems. The first one with minimum phase and the second as all pass. All pass system has been introduced in previous lecture notes. Okay, so we write h of z to be equal to h minimum phase of z times h all pass of z. Okay? For the example above, the zero of the system at z be equal to 1.5 has caused the system h of z to not have the minimum phase. So we have to put this zero in the all pass group or all pass set, meaning that h all pass of z should carry the zero outside the unit circle. Okay, 1 minus 1.5 z minus 1, and the flipped version of numerator will appear here at the denominator. Okay, you see, minus 0.5 plus z minus 1. Okay, which is equal to minus 2 over 3 plus z to the power of minus 1 over 1 minus 2 over 3 times z minus 1. That's it. That's the all pass section created. Starting from unwanted 0 or which is located at the outside of the unit circle and generating a necessary denominator, which is flip version of numerator. That's it. Okay, therefore, what is left for minimum phase? H minimum phase of z will be equal to h of z over h all pass of z, which will be equal to 1 minus 0.5 z minus 1, acceptable 0 inside unit circle, times unwanted 0 over 1 minus z minus 1 plus 0.5 z minus 2 times minus 1.5 plus z minus 1 over 1 minus 1.5 z minus 1. Okay, it's related to h all pass of z, which will lead to having 1 minus 0.5 z minus 1 times minus 1.5 plus z minus 1 over the same story for denominator. Okay? So you have defined the minimum phase part of the system. Now there is a 0 at 0.5, as we said it earlier, and a new 0 at 2 over 3. Okay. Which is inside the unit circle. Now, properties of a system with minimum phase. Consider a system with minimum phase, h minimum phase of z, for any causal system, h of omega, with the same frequency response of apps of h omega be equal to apps of h minimum phase of omega. The group delay for h of omega is greater than or equal to the group delay for h minimum phase of omega. Group delay will later be explained. Don't worry about it. For instance, that is, the system with minimum phase has the lowest processing delay among all systems with the same frequency response. Now, for any arbitrary integer we have m greater than 0 or equal to 0, we'll have summation from n from 0 up to capital M apps of h of n to the power of 2 will be less than or equal to the same for minimum phase. Okay? That is, for the system with the minimum phase, the energy concentration of the impulse response has the largest value around n being equal to 0. Moreover, it means the smallest energy delay. That's the property of minimum phase. Now, digital filter. A filter is a system or network that selectively modifies the waveform, amplitude, frequency, and or phase frequency characteristics of a signal in a desired manner. Right. Conventional goals include improving the quality of a signal, for example, removing or reducing noise, extracting information from signals, or separating two or more signals that have already been, for example, concatenated to pass through a telecommunications channel. Right? A digital filter is a mathematical algorithm implemented in hardware and or software that operates on a digital input signal to produce a digital output signal. In order to achieve a filtering goal, the term digital filter refers to the specific hardware or software routine that performs the filtering algorithm. Most digital filters operate on digitized analog signals or only on numbers that represent some variables stored in a computer memory. Okay. Now, process of a digital filter design. Determining the type of filter, designing pole zero values or coefficients of the filter. When filtering is to be done in hardware, including a fixed point DSP microprocessor, additional steps are involved. Otherwise, just these two steps suffice. The third step, choosing an implementation structure, analysis of finite word length, and moreover, filter implementation as hardware elements. Now, filter specifications in the frequency domain. The first step in design is to obtain a complete specification. Usually, it includes the amplitude of the frequency response of the filter. This step may also include the requirements on the phase response and implementation constraints, including the employed hardware, the number of bits in the digitized signal, the sampling rate, the minimum signal to noise ratio SNR, etc. Normally, the frequency response of the filter is determined by the passband and stopband frequency ranges and the minimum attenuation of the stopband and the maximum allowable ripple in the passband. FIR and IIR design. The most important decision about filter design is whether to use a FIR or IIR filter. Which one is suitable? It will affect the characteristics of the filter and determine the design method to be used. Some of the questions that should be considered in order to choose between the two are as follows. Linear phase. A filter with linear phase exhibits the same delay at all frequencies. Okay? This ensures a minimal distortion in the time domain properties. The nonlinear phase can have a serious effect on the signaling pulses used in data communication systems, but it will have the least effect on the intelligibility of speech signals. Okay? FIR filters can be easily designed to have linear phase. If the filter is supposed to have a linear phase, then the FIR one is usually more suitable. What about the efficiency? A filter implemented using poles, that is IIR filters, can have a sharper transition region than a filter with the same degree of zeros, FIR filter. Okay? An IIR filter can therefore be designed to meet the same amplitude response specification using fewer delay elements and fewer multipliers. An IIR filter is suitable if minimum memory and multipliers are to be used in its implementation. Okay? On the other hand, FIR filters can be implemented by fast convolution using FFT. Due to the long processing time, FIR filters are usually used for non-real-time applications, meaning offline processing. In contrast, IIR filters are used in fast or real-time applications. That's very important. Stability. Since an FIR filter has no feedback elements and no poles, other than the poles at the origin, we mentioned it earlier, it's always stable because it has a very limited terms in impulse response. However, IIR has unlimited terms in impulse response in time domain. Hopefully, we hope that it will tend to limited values or zero. Otherwise, IIR will be unstable. Anyhow, an IIR filter can become unstable under special conditions. For example, if the input causes arithmetic overflow. In such cases, FIR filter is preferred. Now, converting from analog filters. That's a tricky way, tempting. Some designs for analog have already been done. Can we use them in digital environment? Very tempting idea. Okay? Conventional analog filters in the S domain, Laplace domain, are expressed as fractional functions and have poles. Definitely, all types of IIR filters are analog filters are IIR. No doubt about it. When such designs are converted to their digital equivalent, the result is an IIR filter. For example, Butterworth, Chebyshev, or elliptic or blah blah. If you are familiar with analog design. Okay. Pole and zero estimation. The most critical part of the design process is determining the locations of the poles and or zeros of the filter transfer function. Regarding whether the filter should be FIR or IIR, several design methods are available and the choice of one depends on the specifications to be met. We will use the optimized Parks-McClellan algorithm to design FIR filters with an equi-ripple amplitude response. It's optimal because the filter meets the design requirements using the minimum number of zeros. So the best technique for FIR design is using Parks-McClellan technique. Of course, we will discuss other types of designs as well. For example, window-based filtering for FIR. But here you see the most important technique for FIR design. Okay? To design the IIR, the bilinear Z transform or BZT method is used as the best solution, okay? To convert the transfer functions of the analog domain S, Butterworth, Chebyshev, elliptic, into the transfer functions in the Z domain with the same amplitude in frequency responses. Okay. We will explain them in detail later. Now, implementation structures. If the filter is to be implemented on a general-purpose computer with floating-point hardware, then the choice of pole zeros or filter coefficients usually completes the design. Okay? However, most digital filters are implemented with DSP microprocessors or single-purpose hardware using integer arithmetic with approximately a few bits of precision. I myself have designed the techniques using FPGA as well. But here in this lecture notes, I won't explain it. Anyhow, a few bits of precision, for example, 16 bits. Due to the quantization of coefficients and round-off calculation errors, the structure of the filter, that is, the sequence of steps used to calculate the result, can have a significant effect on the efficiency of the filter. The details of implementation depend on sampling speed, filter complexity, and whether real-time operation is requested. Okay? For low sampling speeds or offline analysis, common computers can be used. Laptop, desktop. Single-purpose DSP microprocessors are used for audio frequencies. They have spatial features such as single cycle, multiply, accumulate instructions, and they have dual memory buses that speed up common DSP algorithms such as FIR and FFT operations. For fast applications such as video, custom designed hardware should be used. It means more money, expensive designs. Okay. Finite word length effects. It comes up when the number of bits to represent a number is limited. A digital filter using integer hardware must quantize the filter coefficients to a fixed number of bits. Also, these coefficients should be scaled to avoid overflow. Quantization changes the effective values of the coefficients and therefore must be re-evaluated with the quantized and scaled coefficients to ensure that the requirements are still met. Description of filter requirements. For frequency selective filters, such as low pass, high pass, blah blah, specifications are often considered in the frequency domain and in the form of tolerance schemes. Okay. In the pass band, the amplitude response has a peak deviation equal to delta P, and in the stop band, it has a maximum deviation called delta S. Okay. The width of the transition region determines how sharp the filter is. The amplitude response decreases uniformly from the pass band to the stop band in this region. It means a transition region. Okay? Below are the key parameters. Passband deviation, delta P. Stop band deviation, delta S. Passband edge frequency, FP. Okay? Sometimes the cutoff frequency, FC, is used instead of FP. Okay? You don't need to worry about it. You have lots of problems to think. So ignore about FP or FC to be used. They are near each other. The stop band edge frequency is denoted as Fs. Please be careful about capital F, which stands for sampling frequency. Okay? Now, here you see a tolerance scheme related to a low pass FIR filter. Okay? Low pass FIR filter. Pass band having some repels playing role from 1 minus delta P up to 1 plus delta P. Okay? And a stop band starting from omega S or Fs up to pi or half Fs. It's called stop band. And in the middle, you see the transition region. Okay? So, it's the tolerance scheme for a low pass filter. I invite you to draw the figure for high pass, band pass, and band stop too as take home. Okay? Figure 5.24, we just explained it. And the next one demonstrate the tolerance scheme for low pass FIR and IIR filters respectively. What about IIR? The tolerance scheme somehow differs from FIR. Here you see the top is called a normalized one, and the bottom inside passband, of course, is equal to 1 over square root of 1 plus epsilon to the power of 2. Okay? Here it's passband. And stop band 1 over A, or somehow related to delta S. So omega passband, omega stop band. Here it's called transition region or transition band. Okay.